Hi, in this video we will do an example for optimization. We want to maximize the area of a rectangle inscribed inside a circle of radius r. So we have a circle of radius r and we want to inscribe a rectangle inside this. You see, there are different rectangles you can inscribe inside a circle, and we want to maximize the area. The quantities we are dealing with here is first area of the rectangle, and we know that it depends on the width and length of the rectangle. So width and length of a rectangle. So at least these are the things, the quantities we have to deal with. Well, let me call width x, the length y, and then the area, let me just write a is equal to x y. Length times width, yes. But we cannot work with two variables. We have to make it one variable. In other words, there's a relation between x and y. X and y. What is that? So if you see the diagonal of this such a rectangle is going to be diameter of the circle. So if the radius is r, basically we have a right triangle with sides x, y, and 2r. Then the relation between x and y is given by a Pythagorean theorem, which says x squared plus y squared is equal to 2r squared, which is 4r squared. Well, we can write one of these variables in terms of the other one, which is 4r squared minus x squared. And now we have something here, that if we combine these two, the function to be maximized is a x times y, so I can write x. For y, I can use this relation we found for r squared minus x squared. And this way, it is going to be a function of x. And while our independent variable is x, the domain for x is... Okay, see, when you have a circle, this x can get different values. The highest value it can get very close to be the diameter. So let me just say it max can go up to 2r. But if it becomes 2r, it is not rectangle anymore. So the real domain we are going to deal with is going to be open to r, and on the other hand, we know that r can be any positive number. Well, if you look at this function, at these two endpoints, this is continuous, and actually what we can do is we can replace this domain with the closed interval, such that we can use the facts about the absolute max mean. So then, well, it comes to find max, absolute max of ax in interval 0 to r. First, we need critical numbers. So a prime x is going to be, just use product rule, 4r squared minus x squared plus x times minus 2x to 4r squared minus x squared. Well, we need to simplify this. First of all, we can cancel that and then find common denominator. The first part times the denominator here, it will be 4r squared minus x squared. There's another x squared here, so this will be 2, sorry, minus 2x squared. And set a prime equal to 0. That means that the numerator needs to be equal to 0. And from there, we have x squared equals to r squared. And, sorry, this is not 2, this is 4. And then as a result of this, this is just 2r squared. And then you solve this, you get x is equal to root 2r and x is equal to minus root 2r. But this is not in the interval of study, so we won't take that one. So we have one critical number in the interval, 2 endpoints, and we plug in those values. A at root 2r is going to be equal to root 2r 4r squared minus root 2r squared, the whole thing, this will be 2r squared. And that will give us root 2r times root 2r, which is 2r squared. A at 0 is, well, 0. And A at 2r is 0. We have 3 values, and the maximum, absolute max, will be the one which has the highest value. So the max area of such rectangle is when the width is root 2r, and actually you plug in it here, you notice that that will give you also y equals the same thing. In other words, your rectangle needs to be a square with value, just plug it in. So a of root 2r, which we found is 2r squared. So the maximum area of such rectangle is twice as r squared. Okay.